Angular motion, in which we cover angular kinematics, torque, energy in rotational motion, and angular momentum. In this particular video, we cover or focus on angular kinematics. A body moving in a circle is considered to be undergoing circular motion, whereas a rotating body or a spinning object is undergoing rotational motion. For both motions, we measure the motion in terms of angular motion, in terms of angle traversed. Hence, we have angular motion. And for angular kinematics, let's first look at the basic variables by which we measure the motion of the object. Just like in linear kinematics or motion in a straight line kinematics, which measures or which looks at the motion of the object in terms of displacement, velocity, and acceleration. In angular kinematics, we look at angular displacement or angular position, angular velocity, and angular acceleration. So let's consider an object moving in a circle, going from one position to the other, from position 1 to position 2. The object travels arc length x, traversing an angle of theta. Note that the angle theta is measured in terms of radians. Arc length x is equal to angle theta multiplied by the radius. From here, we get an equation for the angular position of the object. Theta is equal to plus minus x over r. The positive, negative sign refers to the two possible directions that the object may move. It may move in the positive direction or it may move in the negative direction. For our course, positive direction is counterclockwise direction, while the negative direction is clockwise direction. Angular displacement is change in angular position. Angular displacement is equal to final angular position minus initial angular position. Delta theta is equal to theta minus theta naught. Theta naught being theta initial. If we get the rate of change of angular position, d theta over dt, we have angular velocity omega. Omega is equal to d theta over dt, which is equal to plus minus v over r. The unit for angular velocity is radian per second. Average angular velocity is equal to angular displacement divided by change in time, delta theta over delta t. And if we get the rate of change of angular velocity, we have angular acceleration alpha. Alpha is equal to d omega over dt, which in turn is equal to plus minus a over r. Here, v is tangential velocity or tangential speed, while a is tangential acceleration. Again, the plus minus sign refers to the two possible directions that the object may move, positive direction or counterclockwise direction, and negative direction or clockwise direction. The unit for angular acceleration is radians per second squared. Just like in linear kinematics, motion in a straight line, the type of motion that an object will experience will depend upon the acceleration of the object. For motion in a straight line, you have uniform motion, uniform acceleration, and non-uniform acceleration. For angular motion, we have uniform circular motion, uniform angular acceleration, and non-uniform angular acceleration. For uniform circular motion, the angular acceleration is constant at 0, which means that the angular velocity is constant. Angular velocity is constant, just equal to the equation for the average angular velocity, displacement, divided by time. For uniform angular acceleration, the angular acceleration is likewise constant, but this time it is constant at a non-zero value. And we have four equations that we can use to analyze the motion of the object. Just like in linear motion, motion in a straight line, uniform acceleration, we see that the equations for uniform angular acceleration follows the same equation form as in the linear kinematics. You have final velocity is equal to initial velocity plus acceleration times time. Position or change in position is equal to initial velocity times time plus 1/2 acceleration times t squared. Final velocity squared is equal to initial velocity squared plus 2 times acceleration times position or displacement. And you have final average velocity is equal to displacement divided by time, which is also equal to final velocity plus initial velocity divided by 2. For non-uniform angular acceleration, the angular acceleration is not constant. Hence, we have to go back to the two basic equations for acceleration and velocity. Angular acceleration is equal to rate of change of angular velocity, whereas angular velocity is equal to rate of change of angular position. Depending on the problem, you might have to integrate or differentiate. Uniform circular motion, uniform angular acceleration, non-uniform angular acceleration. As you can see, if you recall your equations for motion in a straight line kinematics, you will recognize that the equations for angular kinematics, as I have mentioned earlier, these equations follow the same equation form as the linear motion kinematics. Therefore, these equations are relatively easy to remember as long as you remember the equations for your linear kinematics. All you need to do is just replace the variables with their rotational counterparts, with their angular counterparts. Replace x with theta, replace v with omega, and replace a with alpha, and you have your angular kinematics equations. And that's basically it for angular kinematics. We'll cover examples in a later video.